This glowing grid of server racks represents the true physical mass of a large language model. When we talk about an LLM's parameter count, we are not talking about an abstract algorithm. Every single parameter is a floating point value that occupies exact physical space inside a device's video RAM. To simply load a baseline 8 billion parameter model at 16-bit precision, you need 16 gigabytes of physical memory. That is the hardware requirement just to let the model sit completely idle. But sitting idle is very different from executing a prompt. Model execution splits into two distinct hardware phases: the compute-bound prefill phase and the memory-bound decode phase. During the prefill phase, the model processes your input prompt. This runs efficiently because the GPU can pack its execution units with massive, simultaneous matrix multiplications. The chips are actively doing math. Treating model size strictly as a measure of cognitive capability ignores the physical reality of the hardware. The physical memory footprint creates a hard ceiling on what you can actually run on a local device. During decoding, to generate a single word, every weight matrix is fetched from the deep orange VRAM, pushed through this narrow memory bus, and delivered to the cyan execution units. The processor spends most clock cycles idle, waiting for parameters to physically cross. If you try to run a 400 billion parameter model instead of an 8 billion parameter model on identical hardware, generation speed collapses. The processor has to drag 800 gigabytes of data across that bus for every single step. The sheer volume of data transfer cripples throughput. True optimization for edge devices requires mathematically restructuring continuous algorithms into bounded, spatially aligned operations. High-level software abstraction prevents fast on-device inference. To make these models run efficiently, developers must align their algorithms with the strict physical geometry of ARM and NPU architectures. Standard high-level programming languages, like a basic Kotlin loop, force the CPU into sequential scalar processing. This mode computes exactly one instruction per data element. To bypass this bottleneck, developers map linear algebra directly to the hardware using single instruction, multiple data, or SIMD. This diagram illustrates SIMD. By restructuring data into contiguous blocks, ARM Neon hardware registers load multiple data points into parallel lanes. Look at the vector multiply accumulate operation. The hardware executes the dot product math across all loaded lanes in one instant flash. Mapping equations directly to SIMD vectorization stops the software from wasting physical CPU execution lanes. Mathematical alignment transforms directly into raw inference speed. Executing continuous floating-point math on mobile chips demands high power and incurs massive memory bandwidth penalties, draining device batteries rapidly. This formula maps continuous real numbers to discrete integers. The yellow scale factor and purple 0 point adjust these values. By dividing parameters through the scale factor, it compresses the matrice's physical memory footprint by a factor of 4, collapsing into a dense 8-bit integer layout. Shifting the matrices to an 8-bit execution path inherently avoids the deep VRAM bottleneck observed earlier. The total volume of data crossing the bus drops significantly. This mapping also unlocks the ultra-fast ARM integer dot product instruction sets, natively built into mobile silicon, executing math far faster than floating-point calculations. Quantization transforms the computational requirements of the model. By shifting to 8-bit integers, the hardware utilizes specialized dot product instructions built into the silicon, bypassing energy-heavy floating-point units. Hardware does not fetch single bytes from RAM. Instead, it pulls 64-byte chunks of data into local cache lines. This grid shows the cache thrashing caused by naive row-column matrix multiplication. Standard traversal forces the CPU to jump across memory addresses, triggering constant cache misses. To ensure spatial memory locality, developers implement matrix tiling. The massive matrix is cleanly divided into smaller micromatrices, calculated to fit within the level 1 cache. The fetch lines smoothly process spatially adjacent data side by side, eliminating wait time and keeping execution units saturated. Performance relies on the spatial geometry of memory. When data is not physically adjacent, the processor spends more time waiting for the bus than executing the math. Relying on large static transformation matrices or lookup tables creates a severe execution hazard, bogging down mobile NPU logic. This equation represents singular value decomposition, a mathematical technique applied during the build phase to structurally reduce algorithmic complexity. Factorizing the matrix splits it algebraically, stripping out redundant dimensions while preserving the core logical boundaries. The original operational footprint requires multiplying every row by every column. The low-rank approximated footprint replaces that massive calculation with two significantly smaller ones, reducing the total operations required. Singular value decomposition proves a strict rule of on-device optimization. The most effective way to speed up mobile execution is to mathematically erase the work before the code is ever compiled. Moving past raw mathematical compression, modern architectural design tackles the specific memory constraints of hardware like 16-gigabyte consumer laptops. The mixture of experts architecture decouples an LLM's total parameters from its active computation footprint. This sprawling grid represents a model's total capacity. By sharding the feed-forward network into distinct experts, a top-K router selects and illuminates only a highly specific fraction of parameters per token. This exact routing allows a model like the Gemma 426B to execute using only 3.8 billion active parameters per pass. It delivers the reasoning depth of a mid-sized model at the execution speed of a much smaller one. Mixture of experts enables high-capacity models to function on edge devices by keeping the majority of weights in VRAM while only routing vectors through a specific subset of active parameters. Ultimately, deploying an on-device model requires matching your algorithmic complexity directly to the physical video RAM envelope. For mobile edge devices, the structurally compact Gemma 4 E2B variant dominates deployment because it relies on fast lookup tables and efficient integer math. This layout shows why the MOE26B model is the enterprise sweet spot. It handles complex agentic workflows, routing directly to the laptop tier without choking the unified memory bus. Meanwhile, heavy, dense parameter matrices must be reserved exclusively for full workstations, capable of running novel, multi-step counterfactual logic. Raw parameter count is an incomplete metric for performance. On-device efficiency depends on how precisely an engineer can align mathematical structures with the constraints of the chip.